Today we are discussing the classification of matter. These are your learning targets. And remember, anytime during this video, you can pause, you can fast forward, you can rewind. Now, previously, you probably remember classifying substances by their states of matter. Is this a solid? Is this a liquid? Is this a gas? And so what do I mean by substances? I'm really talking about anything around you. Your water bottle, your cup of paper, your drink. These are all substances. And in chemistry, we're also talking about at the atomic level, right? We're talking about elements like carbon and oxygen, and these are all substances. So to remind you what this looks like at an atomic level, let's take a look at neon. This is neon at its solid state. Notice that the atoms are still moving, right? Just because it's solid doesn't mean that they're still or frozen or anything like that. This is neon at its liquid state, and this is neon at its gas state. Now you probably remember water from biology, so we can take a look at that. Water in its solid state, water in its liquid state, and water in its gas state, right? And how do we change states? Remember, we need to heat it up or we need to cool it down. In science, it's important to know that all solids are not the same, all liquids are not the same, and all gases are not the same. Take a look at gold and fool's gold. Can you tell the difference? Can you tell which one is real gold? Now, just by looking at it, there are lots of similarities, right? And you can probably figure out some differences as well. You can probably point out some differences as well. Now, if we get to the atomic level, things are going to be very different. So it's important to know why all liquids are not the same, why some substances are purer than others in terms of their chemical makeup or composition. So what is chemistry? Chemistry is the study of matter and the changes that it undergoes. All of this around us and what you see is chemistry. Right? Matter is anything that has mass and takes up space. Anything that has mass and occupies volume. And on the basis of composition, matter is divided into pure substances or mixtures. I guess a better way to say that is matter is classified as pure substances and mixtures. So we have this flowchart here that we're going to fill out. So matter is classified as pure substances or mixtures. So the difference between pure substances and mixtures can be seen in these pictures right here. So you know that a substance is a pure substance because all the particles are identical. If you look at this picture, it consists of one type of atom. If you take a look at this picture, it consists of the same exact particle, right? There are multiple atoms in here, but it's the same type of particle throughout the substance. Whereas mixtures will contain different types of particles. So if you take a look at these pictures, the one on the left, it has two different types of atoms, okay? Not joined together or anything like that, just two different types of atoms in this picture here. Whereas this one has how many different types of particles? It has 1, 2, 3 different types of particles all together in one. So these are different types of particles that are present. Again, here, same, right? This is the same in this substance, same in this substance. These are different. 2 different types of particles, 3 different types of particles. Let's take a look at the pure substances first. We can further classify pure substances as elements and compounds. But first, let's take a look at elements. Elements are made from one type of atom. Elements are a pure substance that cannot be separated into simpler substances. In other words, it can't be broken down into smaller particles. So if you have copper wire, it is made up of copper. Copper is the atom that it's made up of, right? Aluminum foil it is made up of aluminum. You can't break down these elements any further. Copper is copper, aluminum is aluminum, gold is gold, right? If you were to grind up that gold nugget until it's powder, it will still remain gold, okay? You can tell that a substance is an element in terms of the chemical formula by looking at our periodic table. If you can find the element on the periodic table, then you know that you have an element. In terms of the chemical formula or the symbol, it has one or two letters. The first letter is always, always, always capital letter. The second letter is a lowercase letter. Now, it might not always have a second letter, right? But if it does, it's a lowercase letter. So for example, we have potassium, that's K, calcium is Ca, and carbon is C. Now we can further classify the elements as monatomic elements or diatomic elements. Monatomic, what does mono mean? Mono means one. What does atomic mean? Atom, one atom. Diatomic, what does di mean? Di means two. So two atoms, and there's only 7 elements that are diatomic. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. So look at the chemical formula. What do you notice about all of these diatomic elements? They have a subscript 2 to indicate that they come as a pair. So this is just, it happens naturally. It's in nature, right? When we talk about oxygen, we're talking about O2. We're not just talking about O by itself, okay? So oxygen in the air is O2. To help you remember the diatomic elements, just remember Brinkelhoff. Brinkelhoff is not a name, it's not a scientist, it's not even an object. It's just, if you were to put these 7 diatomic elements together, it spells out Brinkelhoff to help you remember. Okay, so back on our notes, we're going to fill in our monatomic and diatomic elements. Okay, now let's take a look at compounds. Compounds are a combination of 2 or more different elements that are combined chemically. So you got to do a chemical reaction. You can't just physically put them together. So when you have a compound, you can't even physically take it apart. You have to separate them chemically. Again, it has to go through some kind of chemical reaction. Okay? So the properties of compounds are different than the properties of the elements it is made up of. For example, we have sodium, that's really a metal, and chlorine, that's a gas. But when you put them together chemically, so after it goes through a chemical reaction, we have sodium chloride. And you guys know what sodium chloride is. That's salt, table salt, right? So the properties of the elements are completely different from the properties of the compounds. You get something completely new, okay? You can think of properties like characteristics, all right? In terms of the chemical formula or the symbol, compounds contain more than one capital letter. So remember, elements, if it's just an element, it's just one capital letter, and whatever, if there are other letters there in the symbol, then it's a lowercase letter. But compounds, you have at least 2 capital letters, right? So if we take a look at NaCl, we have how many elements here? We have 2 elements, sodium and chlorine. What about H2O? How many elements do we have in this compound? We have 2, hydrogen and oxygen. How about HCl? Again, we have 2 elements, hydrogen and chlorine. How about H2SO4? How many elements do we have in this compound? We have 3, hydrogen, sulfur, and oxygen. Okay, so every time you have a different element, you're going to have a capital letter. At the atomic level, it might look like this. Okay, so you notice that these 2 are together and they're held by a chemical bond. Now let's take a look at mixtures. Mixtures is a combination of two or more pure substances. Mixtures can be separated physically. So think about some different mixtures in our house. We have air, that's a mixture. Can we separate air? Yeah, we have air filters, right? Where it'll separate the dust from the air, and pet hair and pet dander and things like that. What are some other examples of mixtures? If you have a water filter at home, right? Because tap water, it has different minerals, right? And so you are usually, when you use a water filter, you're separating the water from some of the minerals that come in the tap water. Coffee is another example of a mixture, right? So mixtures can be classified further as homogeneous mixtures or homogeneous mixtures and heterogeneous mixtures. Homogeneous mixtures are also known as solutions. So we call homogeneous mixtures solutions as well, okay? So these are mixtures with a uniform composition. Everything looks the same. You can't tell which part is which. So for example, if you have salt water, you can't tell once it's dissolved, once the solid is dissolved, which part is salt and which part is water. So for bronze, you can't tell which part is copper and which part is tin, right? Because those are the two metals that make up bronze, okay? So at a molecular level, homogeneous mixtures look something like this. It's uniform, right? It looks the same. So here I'm just going to use the colors for example. It's like blue, then white, then blue, then white, then blue. It's uniform composition, okay? Heterogeneous mixtures, there's no uniform composition. The individual substances remain distinct. So for example, let's say I have sand and water and I'm really trying to mix it together. Well, what's going to happen eventually? They're going to separate, right? So this, on a molecular level, is an example of a heterogeneous mixture. You see how random it looks? Okay. So let's take a look at these two examples. Can you tell which one is heterogeneous and which one is homogeneous? Let's take a look at the piece of rock. Is that homogeneous or heterogeneous? That's heterogeneous. Can you see the different layers? Let's do some examples together. We're going to take a look at these 4 different substances, and we're going to classify them as pure substance or mixture, and then further classify them as element or compound or homogeneous or heterogeneous mixture. So let's take a look at our first substance, KMnO4, potassium permanganate. These are potassium permanganate crystals. So sometimes it might be better to classify them as element, compound, or homogeneous or heterogeneous first, especially because you might not be able to tell if it's a pure substance or mixture given a picture. So let's take a look at the chemical formula or the symbol. You'll notice that it contains 3 different elements. How did I know that? Because I see 3 different capital letters, K, M, and O. So here we have potassium, here we have manganese, and here is oxygen. So this I know is a compound because it's 3 elements together and there's no space in between. There's no plus sign or and sign in between these letters. So I know that these are all held by a chemical bond. So that's what a chemical formula will tell me. So if it's a compound, that is a pure substance. Let's take a look at our second example. Potassium permanganate solution, KMnO4 and water. Well, this contains 2 different substances, and that is a mixture. Now, if we take a look at the picture, can you see different layers in it? What you see on the bottom there, that's probably more of a reflection. So no, there are no different layers in that, so that is a homogeneous mixture. What about the Greek salad? This one was probably very easy for you. You can see the different components that make up the salad. So yes, this is a mixture, and it is heterogeneous. You can tell what what is where the onions are, where the olives are, where the tomatoes are, where the cheese is, and the lettuce, right? How about the last one, magnesium, Mg, capital Mg. This is an element. It can be found on the periodic table, and therefore it is a pure substance. Now, real quick before we end this video, if I say that something is a pure substance, can it be homogeneous? No, it cannot, right? Pure substances can only be further classified as elements or compounds, okay? If something is a mixture, can I say that it can be further classified as elements? No, it cannot. Mixtures can be further classified as homogeneous or heterogeneous mixtures. Now, can the mixtures contain elements and contain compounds? Yes. Different elements or elements and compounds can make up homogeneous and heterogeneous mixtures. Now, heterogeneous mixtures can be further classified as suspensions and colloids. Suspension is a mixture from which particles settle out upon standing. So you have sand and water. What's going to happen after you mix it up and put it on the table? They're going to separate. The sand is going to fall to the bottom and the water will remain on top. The particles of suspensions are much larger than that of solutions. Remember, solution is another word for homogeneous mixtures. Colloid is a mixture from which particles do not settle out upon standing. So the particles of colloids are smaller than that of suspension, but larger than that of solution. So for example, like glue, gelatin, and milk. Now I'm going to show you a video just to give you some visuals.
So what is a suspension? Suspension is a heterogeneous mixture where solid particles do not dissolve in liquid. No matter how hard you shake or stir, think of suspended particles as stubborn substances not willing to dissolve in a solution. They just settle down and form distinct layers of sand and water. But why don't you see layers in a solution such as lemon juice? The answer lies in the size. The solute particles in lemon juice are very tiny and they mix very well with water, which makes them disappear between water molecules. The solute particles of a true solution are actually less than 1 nanometer in size. We see the entire solution as a single uniform layer, where the solute particles become invisible. But the sand particles in a sand-water mixture are clearly visible. That means the solute particles in a suspension are much larger than solute particles in a true solution, more than 1,000 times larger. Neither does flour seem to settle down at the bottom of the glass, nor does it dissolve completely like in a true solution. What we have now is a solution where flour is dispersed in water. A solution like this is called a colloidal solution or simply a colloid. A colloidal solution is a heterogeneous mixture like a suspension, but appears somewhat like a true solution. So, a colloidal solution is midway between a suspension and a true solution. Does it also mean that the particle size of colloids is in between that of a true solution and suspension? Yes. The particles in a colloidal solution are not as small as the particles in a true solution, or as large as the particles in a suspension. They are in between. To be more specific, the particle size ranges from 1 nanometer to 1,000 nanometer.
Now there's a phenomenon called the Tyndall effect, and heterogeneous mixtures exhibit the Tyndall effect. So the Tyndall effect is a scattering of light. So ordinarily you can't see a beam of sunlight unless the light passes through the particles of like water or dust in the air. Then these particles are big enough to scatter the sunlight, right? So I'm talking about like that path of light that you might be able to see maybe coming through your window, or even sometimes if you look at the sky. So similarly, a beam of light is visible as it passes through a colloid and a suspension. But solutions, homogeneous mixtures, do not exhibit the Tyndall effect because the particles in solutions are too small to scatter light. I'm going to show you this video to show you what I mean.
If we take this mixture of flour and water and pass a beam of light through it, the path of light becomes visible. But the path of light isn't visible through a glass of glucose drink. This is because the particles of colloids have just the right size to scatter light and make its path visible. This is called the Tyndall effect. This interesting phenomena is observed in all colloidal solutions. Based on this, we can define the Tyndall effect as the phenomenon of scattering of light by particles, whereby the path of light becomes visible. I wonder if suspensions show the Tyndall effect or not. Well, they do, but some particles of suspension are large enough to block the path of light. So only those suspensions whose particle size is small enough to scatter light show the Tyndall effect. Hence, we can say that a suspension may or may not show the Tyndall effect depending on the size of the particles. But colloidal solutions always show the Tyndall effect.
So this is what it looks like at the molecular level. The particles in a heterogeneous mixture, they're large enough to scatter the light. So if you were to shine a light through the mixture, then when it hits these larger particles, it scatters. And that's how you see the path of light, the Tyndall effect. So as you can see here, we have a homogeneous mixture, the particles in a homogeneous mixture, and a colloid and a suspension, and you can see that the colloid and suspension are much bigger than that of a homogeneous mixture, right? And so that's how we get the Tyndall effect. When you shine a beam of light through it, the particles are large enough to scatter the light.